Hello there, welcome to the fifth session of the biostatistics course. Today we're going to be talking about estimation. And like the last lecture with probabilities, this might be a bit of a long lecture, but again, we'll try to make up for it with a shorter stata practicum. Okay, so what are we going to talk about today? We're going to talk about the estimation of the mean for continuous data the central limit theorem, which is probably the most important result in all of statistics. We're going to talk about confidence intervals. And the same topics, which are estimation and confidence intervals for a proportion. So CIs, confidence intervals for proportion. Okay. So in the third session, when we talked about probabilities, we talked about calculating probabilities of events if we knew the distribution. In particular, we talked about the binomial distribution and the normal distribution, but in real life we don't know the parameters of a distribution. Remember, the parameters of the binomial were n and p, the number of trials and the probability of success, and the parameters for a normal distribution were mu and sigma, the mean and standard deviation of the normal distribution. So in real life we don't know these parameters. Instead, we take a sample and try to estimate specific parameters. Okay? So again, just to re-emphasize the what we do in sampling, kind of the fundamental idea of statistics is there's a population out there. Here's our population that we want to know something about, but we don't have the time, the resources, the energy, or the need, frankly, to sample every person in that population. A real simple example is, what if we want to know the average height of people in the United States? Well, we're not going to go measure everyone's height. Instead, we can take a much smaller sample that we think is representative and randomly selected. Then we collect the heights of those people in that much smaller sample, and then we can, if we've collected a good representative and random sample, we can draw inferences from our sample mean, x bar, to the mean of the population, mu. And you'll remember this, this notation, this convention, where population parameters get Greek letters like mu, and sample quantities do not get Greek letters. They get kind of ordinary letters, like here, x bar. Okay. So again, the key step in this kind of sampling framework is that you obtain a sample that is both random and representative of the population that you're sampling from. If you have bias in your sampling design, then you'll obviously have bias in your analysis as well. So be sure to keep that in mind. It's actually one of the most difficult things to get a random and representative sample, but it's crucial to being able to make correct inferences. Okay? All right, so now suppose we want to estimate the population mean, mu. How would we do it? Well, we'd obtain a sample, and then we have our x bar, which is the point estimate. Okay? But that only tells us it's a single number that estimates the parameter of interest. So our point estimate for mu is x bar here. But again, we know that since we've only obtained a small sample, there's going to be variability called sampling variability around that. Okay, so that is to say, if I got this sample and I got x bar 1, I could get another sample over here, sample, calculate its mean, x bar 2, and that might give me a different mean than x bar 1. I mean, almost surely will give me a different mean. Okay, so not only do we want the point estimate, x bar or x2, but we also want an interval estimate so that we can incorporate the variability around these estimates. Okay. So again, you'll remember the sample bar, or the sample mean, rather, is calculated as follows. It's the sum from I equals 1 to n of xi divided by n. Now that looks like fancy math, but all it means is add up all the numbers and divide by the number there are. And just to illustrate again with a simple example, if we have the numbers 1, 3, and 4, what this formula is telling me, x1, this is x1, this is x2, and this is x3. So this is just telling me take 1 plus 3 plus 4 divided by n. N is the total number of numbers. So there's 1, 2, 3 numbers. And this is 8/3. Okay? Or 2 2/3. All right. So now again, if we took a second sample, we might get a different number, a different mean, and so on. And we want to incorporate this uncertainty. Okay? This is called sampling variability. By chance, sometimes our sample mean can be high, other times it might be low. And so what we want to do in statistics is to understand the amount of sampling variability. Okay? All right. So let's now look at some admittedly complicated formulas, but hopefully we can work through them and get them to help us along. Here is the mean of the sample mean, okay? So here E, when we write this E, we mean expected value. Okay? So what am I doing here? I'm taking the expected value of the sample mean, okay? So it's kind of the mean of the means, if you will. So if I took, sample 1, sample 1, sample 2, sample 3, sample 4, sample 5, 2, 3, 4, 5, and so on. I kept repeating this process. I would get an x bar 1 here, I'd get an x bar 2 here, x bar 3 here. I'm just taking a bunch of different samples. And then if I took the mean of those means, that would be kind of getting me on the track to the expected value of x bar, okay? So this is the expected value of x bar. Now all I did here was just write expected value and replace x bar here with just the definition, which is add up all the numbers, divide by the number there are, okay? And then through some math that you don't really need to worry about here, we can take the expectation inside of the summation. Don't worry about those details if they don't make sense. And then we know that the expected value of any x sub I is just mu, and we're adding up n of them, so it's n times mu. Then we multiply 1 divided by n times mu equals mu. So this is what statisticians call an unbiased estimate, okay? So if we take the sample mean, it's an unbiased estimate of the population mean, okay? Because the expected value of x bar is equal to mu, the sample mean is an unbiased estimate of the population mean, okay? That's all we're trying to get at here. And again, remember, Greek letters denote population parameters. Mu is the population mean. Okay? So that's why we always calculate the sample mean, because it's an unbiased estimate of the population mean, which is what we're really after. Okay? Now what about the variance of the sample mean? What does that look like? Let me pull up that formula. There it is. And again, don't worry about the math if it's confusing. All we're trying to do is get a variance of the sample mean. And I can do the same thing that I did last time. I just replace x bar with its definition there. And then I play with the variance and summation. I can pull out the 1 over n squared. Okay. Again, don't worry about that. This is just a rule out there that says if you have the variance of a, x, where x is a random variable, and a is just some number, a constant, that's equal to a squared variance of x. Okay, so that's why this 1 over n squared came out here. Okay, and then we can flip through math, we can flip here, take the variance inside the summation, and it turns out the variance of any xi is sigma squared. We're adding up n of them, so we get an n. We had that 1 over n squared, and so we end up with sigma squared over n as the variance of x bar. Okay? So, this is an amazing result, okay? Because, you know, when we obtain a sample, we have many replicates, right? So suppose I'm sampling people's heights, and one person is 5 feet tall, and the other person is 6 feet tall, and the next person is 5.5 feet tall, and the other guy is 5 feet tall, and so on. We could just keep going, and we keep collecting people. Okay? So we can obviously calculate a mean for these and a measure of the variance, the sample standard deviation. Okay, so we can get an x bar, sample mean, we can get a sample standard deviation, s, and so on. What's amazing also is that not only do we know the sample mean, x bar, but we can get a measure of how much variability there is around that sample mean. That's what's here. That's what this formula is doing. So that's a really, really nice result. We only have one sample mean here, and yet we have a measure of how much variability there would be if we were to repeat this experiment many times. So that's a very, very cool result. We only have one sample mean, and yet we know how much it would vary. And not only that, if you look at the formula, you can see that the variance of x bar decreases as the sample size increases, right? So as n gets bigger here, the variance is going to go down because you're dividing by a larger number. And that makes sense, right? As we obtain larger and larger samples, we're more and more sure of our estimates. And so that's why people want to get large samples. But again, we're always constrained by time and resources and things like that. But again, the variance of the sample mean decreases as n increases, as we would expect. If you get a larger sample, you're more sure about your estimates. The variability of the sample mean is smaller. Okay? So now let's try an experiment. Hopefully this will work. I'm going to exit out of here. And so I'm going to enter a web browser window. If you want to go to this web page yourself, hopefully you can read this address. It's the onlinestatbook.com/stat_sim/sampling_dist index.html. Okay, onlinestatbook.com/stat_sim sim/sampling_dist \index.html. Okay, so what are we doing here? This is going to allow us to explore various aspects of sampling distributions. Okay, so let me hit begin. And here we are. So at the very top, you can see the parent population. Okay, so here I am, I'm starting with what looks like a very normal distribution. Okay, and what I'm going to do is I'm going to take a sample of that, a sample of size 5. Okay, so this is the distribution in the population, the parent population. I took a sample of size 5, which is what we do. We take smaller samples, and it turns out there were 2 here, 1 here, 1 here, and 1 here. Those were my 5. Then I took a mean of those 5 points, and I got this blue circle, okay? And so I can just keep repeating that process. Whoops. Another 5 come down, there's a mean. Another 5 come down, there's the mean. Here's another 5 samples I took, there's the mean. And I just keep repeating this process, okay? And so instead of showing these animations and doing it very slowly, I can just click these buttons and it'll do it very quickly for me. So I'm just adding more and more 5 each time, and I'm getting the mean as follows, okay? So what do you notice about the distribution of the means? Now I can just click 1,000. You can see I just added 1,000 samples. You can see that the distribution of the means looks pretty darn normal. But that's not really that surprising because the parent population that we started with was normal. So if I take a bunch of samples from a normal population and then I get the mean of those samples, the distribution of the means is normal. Not that surprising. What if instead of a normal distribution I start off with a uniform distribution? So a uniform just means that between two numbers, all of the numbers are equally likely. So again, I can take samples of size 5 from there, and there's its mean. Here are my 5 points, there's the corresponding mean. I can do that again. There it is, there's my second mean. Just keep repeating this process, and again, I can skip and start doing this more and more quickly. Okay. And just repeating this process over and over. And now let me just add 1,000. And you can see the distribution of the means looks pretty darn normal, even though we started with a parent population that was uniform. Now this is a really, really cool result. So we started with a uniform distribution, took a bunch of samples, and then looked at the distribution of the means, and it looks pretty darn normal. Okay, so I can just keep adding 1,000, and as I keep adding more and more, it keeps looking more and more normal. Okay, so now what if I go with a skewed distribution, something like this? Again, I can take samples of size 5, get a mean, there it is. There's another one that happened to coincide. Then I keep doing this over and over again. Okay, now I'm speeding the process up, adding 5 each, doing 5 reps of 5 each time. Let me just go to 1,000, and you can see, add even 10,000. This looks normal again. Even though I started with a very skewed parent population, my distribution of the means looks really normal. Okay, I can change the number I'm sampling. I was sampling 5 at a time before. What if we do 2? Okay, so instead of 5, there's 2, there's the mean. There's 2, there's the mean. Okay, but again, if I add 1,000, this starts to look pretty darn normal. Okay, and I can even do a crazy distribution. Let me clear everything. I can even do, look at that distribution. That's not like anything I've ever seen. But I can sample from there. Suppose I pick 10 at a time. Here come 10. And there's the mean of those 10. Do another 10. There's the mean of those 10. Okay? Let me speed that process up. Can add 1,000, another 1,000, another 10,000 even. And hey, this looks pretty darn normal. Again, starting with a parent population that is you know, like a crazy distribution, very skewed, not at all symmetric, definitely not normal, we end up with a distribution of means that is normal. So this is a very interesting result. And this thing gets normal much more quickly if we sample, 25 people at a time, as opposed to 10 people at a time. You see it's already normal with samples of size 25. Okay? So basically the takeaway here is that no matter what sort of parent population we start with, even if it's really skewed, as we take samples and calculate their means, the distribution of the means is normal. Okay? So that's a very cool result. Okay? So let me return to here and go full screen. All right. Okay. So this is what we call the central limit theorem. One of the most important results in all of statistics. The central limit theorem. Okay. And what does it say? It says if you take a sample of size n, and n is large, so take a sample of size n from our population, and n is large, the distribution of the sample means that is to say, if we were to repeat the experiment over and over and get a bunch of sample means, the distribution of the sample means is normal. This is crazy. We can even start with a very skewed parent population, but the distribution of the sample means is going to be normal no matter what. And it's not only normal, but its mean is mu, which is the population mean, and its standard deviation, as we saw in this previous slide. Remember, this previous slide showed us the variance was sigma squared over n, which means that to get the standard deviation, standard dev, we just take a big square root over this, so that gives us sigma over root n. Okay? So here it's sigma, standard deviation of sigma over root n. So this is a very amazing result. So when we take a sample, we know the distribution of the sample means. We will never know the distribution of the parent population, but we do know that the distribution of the sample mean is going to be normal with mean mu and standard deviation sigma over root n. Okay? So what does that look like in a picture? It's just telling us that so that the distribution of the sample mean is normal, which I've shown here, based at mu, the population mean, and the variability is sigma, standard deviation is sigma over root n. This is an amazing, amazing result, and it's going to allow us to do lots of cool analyses and tests, okay? So let's talk a little bit more about the standard deviation of the sample means. So the standard deviation of the sample means which we said was sigma over root n. Okay? This is also called the standard error. Okay? So the standard error is the standard deviation of the sample means. Okay? This tells you about the variability in the distribution of the sample means. So it goes down as the sample size goes up. So as n gets bigger, we get larger and larger samples. This whole quantity, we divide by a larger number, so the quantity goes down. Okay? All right. So that's a very, very interesting and helpful result. Okay? And so it's going to help us going forward because remember we said we have an estimate of the population mean through our sample mean, but we also want to incorporate the accuracy of our estimate. Okay? So that was to say that if we, remember we said if we obtain sample 1 here, this is sample 1, then we obtain sample 2 and sample 3, and we keep repeating our experiment, each time we could calculate a sample mean. And we know, just because of sampling variability, that these numbers are going to be different, x bar 1, x bar 2, and so on. And so this number, the standard error, helps us quantify the variability. Okay? So, all this is to set up something that I'm sure you've heard about, which is confidence intervals. Okay. So the definition of a confidence interval is a set of values that we believe are plausible estimates of the population mean based on the sample we've drawn. Okay? So the confidence interval is an interval around our sample mean that allows us to have a certain amount of confidence that the population mean is covered by the interval. Okay? So to construct a confidence interval, we go back to what we learned in the third session about probability. So we're going to start with a standard normal. Remember, a standard normal is one that has mean 0 and standard deviation of 1. And we had this magical number of 1.96, which left 2.5% in the upper tail. Okay, so let's remind ourselves of that through a picture. Remember, this was our standard normal here. Was mean of 0. The variance was 1, so this is about 1. This is about -1, and so on. And so at 1.96, we knew we were cutting off 2.5% of the data here, 2.5%. And then over here at -1.96, we're similarly enclosing another 2.5%. Okay? So using that picture and remembering those things we learned about the standard normal, we can then move to this equation. Okay? So this is so that we know that between -1.96 and 1.96, here are those two values, say. This middle part contains 95% of the data here. And then again, we know that a z, or standard normal, is just equal to, remember we subtract off the mean? Now we're working with x bar. Okay? Remember previously we'd work with x, but now we know the sampling distribution of the sample mean, which is what that little demonstration showed us. And it said that the mean is mu, the population parameter, and the standard deviation is sigma over root n. Okay? So we can now, to get z, equivalent to z is x bar minus mu divided by sigma over root n. Okay? So anytime you have a random variable and you subtract off the mean and then divide by the standard deviation, you get the standard normal. So we're just, we're just kind of working backwards here, okay? So we're starting with a standard normal and working our way back, okay? And so now what we're doing here in the third step between here and here is we're multiplying both sides by sigma over root n. By both sides I mean multiply negative 1.96 times sigma over root n, and then also multiply 1.96 by sigma over root n, then add, then move the x bar, move it to here by subtracting, and move it to here. Again, you have a negative sign here, so everything kind of flips. Don't worry about the algebra, just worry about the concept behind this. And so now we have this thing that looks like a 95% confidence interval for the population mean, right? Okay. So the resulting interval, I'll just write it here. So this interval, x bar minus 1.96 times sigma over root n, comma, so that's one number, you just calculate what that is, comma, x bar plus, remember here I did minus, now I'm going to do plus, 1.96 times sigma over root n. That's our interval, okay? And the way we interpret that is to say we are 95% confident that this interval, so again, we're just starting with our estimate of the population mean, which is x bar in both ways. And here this is incorporating the variability, right? Variability here. And so we're 95% confident that this interval will contain the true population parameter, mu. Okay? So we have to be careful about this. Why didn't I just say that we're 95% sure that this interval will contain mu? I said that we're 95% confident. Okay? So what does that mean? It means that if we select 100 random samples from the population, and we calculated 100 confidence intervals for mu, the population mean, then approximately 95 of the intervals would cover mu, and 5 of them would not. Okay? So that's why we can't just say we're 95% sure that this interval contains mu or it doesn't. Because in actuality, it either contains it or it doesn't. So when we say we're 95% confident, what that means is if we were going to repeat this thing 100 times and create 100 different intervals, then on average 95 of the intervals would contain the true population mean mu and 5 of them would not. Okay? So since this 1.96 here came out because we wanted a 95% confidence interval, right? 1.96 was the number that put 2.5% over here and 2.5% over here. So more generally, we have this formula. This is for any sort of confidence interval. And instead of having 1.96, we now have this z1 minus alpha over 2, okay? So we could construct a 90% confidence interval, a 95%, a 99%, or any other sort of confidence interval that we wanted, okay? So what that would mean, in a 90% confidence interval, we would want the z critical value such that there's 5% enclosed here and 5% enclosed here. We did the example of a 95% confidence interval, so we had to put 2.5% here and 2.5% here. Or we could do a 99% confidence interval and be further even so that we put 0.5% here and the other 0.5% here, okay? And so the numbers that cut off these amounts that we want, those are the z critical values, okay? And so it turns out that for 95%, that's 1.96, okay? All right, so we can create any sort of confidence interval that we want, okay? So again, to emphasize this point, we want to remember that the population mean is not a random variable. The population mean is what it is. It's not random. What is random are the samples that we take, okay? So the interval that we construct is the random variable that's subject to variability. So just to state that once again, the population mean is not a random variable. Suppose again I'm interested in the mean heights for people living in the United States. That's some number. That's some number that I can't know. But it is a number, it's not a random variable. But if I take small samples, the individual samples are random variables, and so are the sample means that I calculate. So when I calculate a confidence interval for the mean, the interval is a random variable, okay? So that's why we do not say that there's a 95% chance that the population mean is in the interval. Instead, we say we are 95%, or whatever, it could be 90% or 99. That's why we say we're 95% confident that the interval covers the population mean. The population mean. Okay? All right. So let's look at this again through another simulation. So let me just exit out of here, go to another web browser. Okay, this is at rice.edu, and I'm going to click on begin. Okay, so in case you can't read this, I'll just read what it says. It says when you click the sample button, 100 samples of the specified size, which is 10, 15, or 20, I can change that here. So right now 10 is selected. When you click the sample button, 100 samples of the specified sample size of 10 will be taken from a population with mean of 50 and standard deviation of 10. Okay? So this is why it's called a simulation. A simulation is something where you know the truth and you kind of conduct an experiment to see what you would have seen if you didn't know the truth, if that makes sense. So here we know that the true population has mean 50 and standard deviation of 10. We know the truth, but we're still taking small samples of it like we would in normal life when we don't know the truth. Okay? So when we click the sample button, 100 samples of the specified size will be taken from a population with mean of 50 and standard deviation of 10. The confidence interval on the mean will be computed for each. Okay, so we're taking 100 samples and computing 100 different confidence intervals for the mean. If the 95% confidence interval contains the population mean of 50, then the line will show the 95% confidence interval in orange and the 99% confidence interval in blue. If the 95% confidence interval does not contain the population mean, then it will be shown in red, and if the 99% confidence interval does not contain the population mean, it will be shown in white. So basically all we want to remember is if one of these confidence intervals does not contain the population mean, it's either going to be red or white, depending on whether it's 95 or 99%. So let me click sample here, and you can see the red ones are where the 95% confidence interval does not contain the true population mean of 50. So there's a couple red ones, and there's a couple white ones too. The white ones are where the 99% confidence interval does not contain it. And here in this table, it's really nice summary of what happened for these 100 confidence intervals. So for the 99% confidence interval, 98 of them contained the true the true population mean, and 2 of them didn't. Meanwhile, for the 95%, 91 of them contained the true population mean, and 9 of them didn't. Okay, so it looks like both of them underperformed a little bit in this first sample of 100. Instead of getting 99 of them in there, we got 98, and instead of getting 95 containing the population mean, we got 91. But we can keep repeating this experiment over and over again, and you can see down here it has the proportion. Now we've achieved 99% here, and we've achieved 95% here as well. Okay, so I can clear this, and instead, if I were taking samples of size 20 instead of 10, you can see I reach those numbers much more quickly. Okay, so this is a cool kind of illustration of the fact that why we call these confidence intervals and why we interpret them as saying we're 95% confident. It's to say if we repeated it 100 times, then 95 of the 100 intervals would contain the true population parameter mean, and 5 of them would not. Okay? All right. Good. So let's return here. Okay. So now let's talk about things that impact the width of the confidence interval. The width of the confidence interval is based on 3 factors. Okay, so let me pull up the equation. There it is. There's our equation. So what are the things that impact the width of the confidence interval? Well, x bar is just, it is what it is. There's no real, we took a sample and it's on both sides, so that's not really affecting the width of the confidence interval. What is affecting the width of the confidence interval, on the other hand, one is the confidence level. Okay, what is that? That's that z factor. Okay, so z 1 minus alpha over 2. Okay, so remember we said we can have a 95% confidence interval, we can have a 99% confidence interval, we can have any sort of, we can have an x% confidence interval, any sort of percent confidence interval that we want. Okay, so what do you think? Do you think a 95% confidence interval is wider, or a 99% confidence interval? Which one of these would be wider? So as it turns out, the 99% confidence interval is wider. Why is that? Because by increasing the level of confidence, we want to be more sure. We want out of 100 intervals that we generate, we want 99 of them to contain the true population parameter. So we want to be more sure. And how can we be more sure? Well, we can make the confidence interval wider. Okay? So similarly, analogously, the 95% confidence interval is narrower. Okay? Because we've said, hey, we can make 5 mistakes out of 100. It's not a big deal. And so by allowing for more mistakes, we can make our interval wider, right? And so I always remember this by thinking about the extreme case. What about a 100% confidence interval? It doesn't matter what you're talking about, but because a 100% confidence interval could be -infinity to infinity. Okay? What is the mean height for men in Botswana? I have a 100% confidence interval. It goes from -infinity to infinity. Now obviously that's not very helpful, but it helps us to understand the concept. So as your confidence level increases, so too does the width of the confidence interval. Okay? What else affects the width? We had 1 was the confidence interval. 2 is the variance, which is in this formula sigma. And that's something that kind of quantifies how different the people are, okay? So if we're measuring something about height again, if there's a lot of variability in height, then the confidence interval is going to be wider. But if a lot of people are very similar in heights, the confidence interval will be shorter, okay? And then the third thing that influences it is here, n. That's our sample size, okay? Sample size n. So how many samples did we use to obtain an estimate of the population mean? Okay, and so as you can see, since this is in the denominator and this is intuitive, as we obtain more and more samples, we're going to get a narrower confidence interval. Remember, narrow confidence intervals are what we're after, because if we didn't care, then here's our wide confidence interval from -infinity to infinity. Okay, so these are the three factors that affect the width of the confidence interval. Now, which of these are in the control of us, the investigators? Which of these three things are under the control of the investigator? Well, it turns out we're in control of the confidence level, right? Because we can choose between 95% or 99% and so on. The variance is not under our control. Okay? People are going to be different or the same or on different measures, but we can't really control that. But the sample size is under our control. Okay? We can always obtain more people, but it comes at a cost of time and resources and so on. Okay? So three things that affect the width of the confidence interval, and we're under control of two of them. You might say that since 95% confidence intervals are kind of the standard in medical literature, you could say that we're not in control of the confidence level here, but theoretically we can always change it. Okay. All right, so now let's work with an example. All right, these are kind of made up data, but suppose we have something where x bar is equal to 54.5 and sigma is equal to 12.1. Okay? Now, if you're a very astute student, you'll notice something kind of tricky that just happened. So I gave you the sample mean here, which is all well and good because we could take a sample and obtain a sample mean, but then I gave you the population standard deviation. Okay, so this relates to a sample, while this relates to a population. How in the world would we ever know the population standard deviation? The answer is we wouldn't know it. So this is just an illustrative example to get us going, and then we'll work up to the real world example where we won't know the population parameter. Okay? All right. So in a case like this, and now suppose we'd collected 252 people, we can just plug these numbers into our formula, and if we do so here, so again, this is a construct that we're going to get very familiar with. So it's x bar minus, and again, it looks like we're working with a 95% confidence interval. And how did I know that? Because of this 1.96. I know that 1.96 puts 2.5% on one side and 2.5% on the other. As such, 1.96, so that this area is 2.5%. Okay, and then here's our sigma, our population standard deviation, divided by root n. Remember, this is that sigma over root n that we learned about from the central limit theorem, that very cool result. And then comma, our sample estimate, again, plus now this time, before it was minus, now it's plus. 1.96, again, because we're in a 95% confidence interval, times sigma over root n, the standard deviation of the sample mean, also known as the standard error. And then we can just calculate these things out, and it turns out this 95% confidence interval goes from 53 to 56. Okay? So hopefully that's clear. Now, if I can just remember, we said if we wanted to construct a 99% confidence interval, that means we want to be more confident, and in order to make sure that more of our intervals contain the true population parameter, we have to make the interval wider. Okay? So let me just show you what that looks like. Oops. Sorry, it's getting crowded here. That's just this. Oops. Okay. So instead of 1.96 now, I use 2.58 as my number. And as a result of that, I get, sorry, this is, but you can see the interval is wider because it goes from 52.5 to 56.5, whereas before it was from 53 to 56. So we now have a wider interval because we have a 99% confidence interval. Okay? All right. Good. So let's carry this example a little bit further forward. Remember, we had said that n, we had collected 252 people. Suppose now instead of 252, we had taken 50, and everything else remained the same. What would our confidence interval look like in that case? Okay, here's what it would be. Everything's the same. This is again a 95% confidence interval. I know that because of this 1.96. Sigma is still the same. Our estimate of the mean is still the same. What has changed is instead of 252 here, we now have 50. And so we have way fewer people in our sample. And the result of that ends up being that we have a correspondingly wider confidence interval. Remember, before it went from 52, I believe, to 56. Now it goes from 51.1 to 57.9. So we have a wider interval because we sampled fewer people, which makes sense. If you put a lot more time and resources and effort into your study, you should get the reward of being more sure about your estimates. Okay? Now let's see what would happen if the variance were to decrease. That's this 12.1. Say we're to decrease from 12.1 to 7.5 here and here. Then you can see if the variance were to go down, then we would get a tighter confidence interval. Okay? So that illustrates all the things that kind of impact the width of a confidence interval. All right, so I promised that we would move to the real world situation in which we don't know the population standard deviation. Remember, in the last example, I gave you sigma, but in real life, we won't know that, right? We won't know the population standard deviation, okay? So if this is the case, which it always is in normal life, where we don't know the population standard deviation, but the underlying data is normal, we can use a distribution called the t-distribution, okay? So this is a confidence interval with t-distribution. Okay, so the entire procedure is the same, but the cutoffs are from a t-distribution. So let me show you the formula. Here it is. Okay, so what has changed? You can see that now, remember before we had here, whoops, sorry about that. Here we had z before. Now we have t, so that's different. We'll talk a little bit more about that. So we're using the t-distribution, but another key part is here we now have s. S is our sample standard deviation, whereas before we had sigma, the population parameter, which we said we'd never know in real life. Okay, so we now, two things have changed. We now have the t-distribution here, and we have s here. Okay, so let's talk a little bit more about the t-distribution. What in the world are we doing? Let me show you a picture. All right, this is the t-distribution with 10 degrees of freedom, which is shown in blue, the top one here. Whoops. And the red one, the one underneath, is a normal distribution. And so you can see that the blue one, the t-distribution, has what we call longer tails, right? Because it's on top over here, it has longer tails here, whereas the normal is lower down here, okay? So the way we express that is we say that the t-distribution has longer tails, okay? Or heavier tails sometimes, okay? So that means that confidence intervals using the t-distribution are wider than confidence intervals using the normal distribution. And that should be the case, right? That should make intuitive sense because we don't know the population standard deviation. We don't know this, and so we estimate it with S, the sample standard deviation. And so because there's uncertainty in both, we want mu, and we're using x bar, and we want sigma, and we're using S. So because there's uncertainty in both of these parameters, that uncertainty is reflected in having wider confidence intervals than if we were to know the population standard deviation as we pretended we did in the examples. Okay? All right. And you'll notice that the t-distribution has this funky parameter. Remember, the parameters of the normal distribution were the mean and the standard deviation. The parameter for a t-distribution is this funky thing called degrees of freedom. Okay? And so I think of degrees of freedom, so you'll see that it'll say things like n-1 degrees of freedom here, n-1. So one way to think about that is, suppose I tell you the mean of a bunch of numbers. Suppose I tell you that the mean is, I don't know, 4, okay? The mean of 3 numbers is 4. And then I tell you x1 is 2, and x2 is 5, and there's only 3 numbers, so x3, okay? So if the mean of these 3 numbers is 4, then that means they should add up to 12, right? So 2 plus 5 is 7. So what I'm missing here is another 5. So I know, even though I collected only 2 of the numbers, because you told me the mean was 4, I know the last one is equal to 5. So that means we had n-1 degrees of freedom. So there were 3 numbers, right? 3 numbers total, n was equal to 3. But we only had n-1 or 2 degrees of freedom. Once I told you what 2 of these were, we knew what the third one had to be, okay? So only 2 of these were free, kind of had the freedom to be anything they wanted to be. once we had two of them locked down and knew the mean, the third one could be determined easily. Okay, so that's a good way to think about what we mean by degrees of freedom. Okay, so as you might expect, if you're following along very nicely, we have this. Okay, so the degrees of freedom. So as the sample size increases, right? So usually we have n minus 1 degrees of freedom. So if you have 2 degrees of freedom, it probably means n equals 2. Here is n equals 11, n equals 101, n equals 1001. Okay, so as the sample size increases, we're going down here, the numbers become much more similar to the normal. Remember, now we have a huge sample of 1001 people, and all of a sudden our t-value for a 95% confidence interval is our old friend 1.96. But however, if we have smaller samples, like here, we have to use larger numbers, which then lead to wider confidence intervals. Okay? So the story is that the t-distribution and normal become very similar as the sample size increases. So therefore, confidence interval construction in large samples can be based on the normal or the t-distribution without much change, even when the standard deviation is estimated. Okay? So if you have a large sample, your t-distribution is going to give you a very similar result to the normal. Okay? So Stata is going to do this for us, and we'll see that in the next practical lecture. We'll calculate confidence intervals using Stata. It'll use the t-distribution. Okay? But when you use a t-distribution, you're assuming that the data come from an underlying normal, just that you don't know the parameters of that normal distribution. Okay. Good. All right, so let's move to the next topic, which is to estimate. We want an estimate for the difference in group means. All right. So far, what do I mean by an estimate for the difference in group means? So far, we focused on estimating the mean for a single sample. Now, we can use similar approaches to estimate the difference in the mean between two groups. Okay? So now we're kind of working up to things of real interest. Okay? This is very common in medical research. Suppose you have a new treatment, you give the treatment to one group, and then you have a placebo or a standard of care that you give to the other group, and you want to estimate the difference in group means. So the mean, whatever your result is, the mean, say, CD4 count in the group that got the new treatment, and the mean versus the mean CD4 count in the group that didn't get the new treatment. Okay. All right, so in order to do that, first we need a point estimate, okay? And as you'd expect, the point estimate is simply the mean in the treated group, for example, minus the mean in the placebo group. That's our point estimate of the difference in group means, okay? Now, what about a confidence interval? Again, we know there's going to be sampling variability. If we were to repeat this experiment a bunch of times, we'd get different quantities for the sample mean of the treated minus the sample mean of the placebo groups. So we want to incorporate that uncertainty through the construction of a confidence interval. Okay? All right, so now I'm going to display another crazy formula. But again, don't worry about the details of the formula, just the general concept, okay? So here in this case, our two groups, one is called MS, that's for people with multiple sclerosis. And then there's the control group, okay? So just like we did last time, we start off with this equation from a standard normal. We know that 95% are contained, of the data are contained between a z critical value of negative 1.96 and one of 1.96. We then work backwards from our standard normal z to, and again, hopefully this is now intuitive. Our point estimate is the difference of the group means minus the population means. Again, subtract off the mean, divide by the standard deviation. Remember before we had sigma over root n for one sample. Now we have two samples and it's sigma over root n1, whoops, plus n2. So that's what this piece is, the denominator. Okay, so that's just the analog of sigma over root n, just extended to two groups. And same thing here, this is just the analog of the sample means extended to two groups. And we do the exact same things that we did before. Multiply both sides of this equation by this stuff, and then move the x bars to the side as well. And then that gives us the confidence interval that we're after down here. Okay, it's so long, we had to write it on two lines. This is just one line here. Okay, so that means what we're after here, hopefully this makes sense, what we're after is a confidence interval for the difference in population means between the two groups. This is what we're after. Okay? And the confidence interval, the lower end of it is this stuff. So our estimate minus the critical value times the standard deviation. So again, this is the general format. Estimate of whatever we're after minus critical value times standard deviation. Okay, so here's our estimate, the difference in the sample means, minus the critical value, this is a 95% confidence interval, times the standard deviation. That's the lower end, and then the upper end is obviously the estimate plus the critical value times the standard deviation. Okay? So it looks like a lot of crazy math, but all we want to do is get the concept out of this. This is just extending what we'd learned for the way to compute a confidence interval for one sample, now for the difference between two groups. And in this case, it was the MS group versus the control group. Okay? And again, you'll notice, just like we started before, we're starting assuming we know the population standard deviation, which we will not know. And so here's our overall formula. Estimate minus critical value times standard deviation. That's this piece. That's the lower bound, and then the upper bound. Lower bound. And then the upper bound is here. It's the same thing, estimate plus critical value times standard deviation. Okay? And again, we say that we're 95% confident that this interval will cover the difference in the means of the two groups. Okay? All right. So hopefully that makes sense. So here's an example if we were to plug in numbers. Okay, suppose x bar in the MS group is 22.3, x bar in the control group is 14.5. We want a 95% confidence interval. Somehow we are amazing and we knew the population standard deviation is equal to 10. We won't know that in real life, so we'll talk about the extensions again. And suppose we'd sampled 30 people in the MS group and 45 in the control group. And then we have all these numbers and we can use them to develop our confidence interval. Okay? And it turns out if you just do the algebra here, this confidence interval goes from 3.2 to 12.4. All right. Okay, so you guessed it, the next thing we're going to move on to is the t distribution for this case. Because again, we will not know the population standard deviation. Okay? So what does that look like? Let me pull up the formula. Here it is. Okay, so we take same sort of thing. Here's our estimate of the difference in group means minus critical value is now coming from a t distribution times, and again now we have s, which is the sample standard deviation rather, times the sample sizes. That's just our s over root n extended to two groups, group 1, group 2, and then times the t because we don't know the population standard deviation. But again, same construct. Just really want to drive this point home. Estimate minus critical value times standard deviation. That's our lower bound, and then the upper bound is the estimate plus the critical value times the standard deviation. Okay? So hopefully the kind of general formula or the general construct for confidence intervals is clear. Okay? So to summarize, the difference in the mean in two groups can be estimated by subtracting the sample means. That's what we did here. That was our estimate. Our estimate for the population difference in means, we estimate by the difference in sample means. And as in the one sample case, we can also calculate confidence intervals for the difference between groups. And we will discuss more specifics regarding the t distribution in future lectures. But for now, we just want to remember that when we don't know the population standard deviation, which is always, we use the t distribution. Okay? All right. So the confidence intervals are going to be, again, we said that biostatistics, like most disciplines, continues to build on itself. So these confidence intervals are going to be related to hypothesis tests, which we're going to cover in the next lecture. Okay? And it's also possible, again, we've constructed confidence intervals now for the mean, or the difference in means between two groups. It's also possible to calculate estimates and confidence intervals for other parts of a distribution, such as the variance. Okay? But more than anything else, Like 99% of the time, you're going to see confidence intervals for the mean. But again, if we wanted them, we could construct confidence intervals for other things. Okay? All right. So, all that was for continuous variables. Okay? It's going to be really important throughout this course that you think about what sort of variables you're dealing with. So all this stuff was for continuous variables. What if we wanted to do estimation for a proportion? Okay? What would that look like? Okay? Suppose we have some treatment, okay? And we want to estimate the proportion of patients who progress, whose disease progresses if they take a treatment, okay? All right, so what we want to do is sample a bunch of people who are on some treatment and then count the number of them whose disease progresses and the number whose disease does not progress, okay? And so the way we write that is as follows. We would say our estimate of the proportion is equal to the number who progress, whose disease progresses, divided by the total number of patients. Okay, so in mathematical terms, we would write p hat. This hat tells me this is an estimate from the sample that I took, a sample estimate of the proportion. Okay, equals x over n. Okay, x is the number who have the event, the number who progress. N is the total number of people. So to get an estimate for the proportion of people whose disease progresses, I just take the number who progress, x, and divide by n. Okay? So that's my point estimate. And so by now, hopefully, you're getting used to this routine. A point estimate is not enough. We want to incorporate the sampling variability or uncertainty, and we do so through the construction of a confidence interval. Okay? But now what's different is that we're dealing with a binary outcome. People either progress or they don't. Okay? And so the number of patients who progress can be described using a binomial distribution, which we learned about. Remember, the binomial applies to cases with two outcomes: progression, no progression, disease, no disease, and so on. Okay? So let's think a little bit again about the binomial distribution. Okay? So remember, the binomial distribution has two parameters, n and p. N is the number of trials. The number of trials. So in this case, it would be the number of people, right? And p is the probability of success. Remember, we said success is not necessarily a good thing. Here, it would be those whose disease progresses, so that's not a good thing. We just mean it to denote that it has two categories: success, failure, progression, no progression, and so on. Okay, so binomial distribution has two parameters, n and p. And so let's take a look at what these distributions look like for a couple different scenarios. Okay, so here is one example. This was generated using n equals 50 whoops, n equals 50, and p equals 0.5. So that means the probability of progression is half, and we collected 50 people here. Okay, so you can see the center of this is right at 25, like we would expect. Whoops. Sorry about that. Okay, it's centered at 25. And you'll also notice that this thing looks pretty darn normal. Right? So this is kind of the distribution function. Now let me go on to a different example. Again, still using n equals 50, but this time let's say the probability of success is 0.25. Okay, so where would you expect the center of this distribution to be? Remember, we said that the expected value for a binomial is equal to n times p. So in this case it would be 50 times 0.25, which is equal to 12.5. So let me show that picture. There it is. You can see it's centered at 12.5, just like we expected. And again, you can see that this thing looks pretty darn normal. So that these graphs show that even with a moderate sample size, the normal distribution reasonably approximates the binomial. Okay? So even if we have a pretty small sample size, here we had 50, not too big, the binomial starts to look pretty darn normal. Okay? So why is that important? Because in order to construct confidence intervals, we can use now a normal approximation. A normal approximation to the binomial. Okay, so if n times p is sufficiently large, then the distribution of the number of successes x is approximately normal. Okay, that's what these two plots showed us back here. Okay, this is just that written out in words. If n times p is sufficiently large, you might ask me, what does sufficiently large mean? That's a very good question. We'll come back to that. So if n times p is sufficiently large, the distribution of the number of successes is approximately normal. Okay? And so if we're going to use a normal distribution, remember we need two parameters, the mean and the standard deviation. So the mean is just n times p. And we'd said before that the variance is equal to n times p times 1 minus p. And so therefore the standard deviation, we can just put a square root on that stuff, n times p times 1 minus p. Okay? So there are the two parameters we need, the mean and the standard deviation. Okay? So here's big Z, which is the standard normal. Remember, we get standard normals when we take a random variable, subtract off its mean, divide by the standard deviation. So x is my random variable. I'll subtract off the mean, which I said was n times p. I'll divide by the standard deviation, which is n times p times 1 minus p. Okay. So now I can do, if I do a little bit of algebra, specifically I'm just going to divide every number in this equation by n, which is a legal move. If I divide everything by the same number, it's fine. So x will be divided by n minus n times p divided by n over square root of n times p times 1 minus p divided by n. Remember, the divided by n is outside the square root. Okay? And before, remember, if I go back a couple slides, remember we said p hat, our estimate of the proportion was x over n, right? So here, when I go back forward, now I have x over n here, right? That's just p hat equals p hat. That's my estimate of the population proportion, okay? Now n times p divided by n, the n's just cancel, leaving me with p, the population proportion, divided by, the way I can get this n into the square root is by squaring it, right? So kind of this piece down here is equal to the square root of n times p times 1 minus p divided by n squared. And so this n cancels with this one of these, and I'm left with square root of p times 1 minus p over n. Okay? So again, you'll see this looks very similar to what we had before, and now it's our friend, the standard normal. Okay? So now I'll show the derivation kind of in a technical way. Again, don't worry if you don't follow every single step of this. The idea is just to get the general gist of what's going on. Okay? So we start off with what we've known since the last lecture, and that is if you have a standard normal z and the cutoffs of negative 1.96 and 1.96 enclose 95% of the data. Now, through our last step, we learned that z is also equal to this thing. Okay? Remember, p hat is our estimate of the population proportion, while p is the population proportion. Unfortunately, this is a case where if we followed the same rules as before, this p would be a Greek letter, because we always use Greek letters for population proportions. But here in this case, it doesn't have a corresponding population proportion. So we just work with p. And then we do the same things we did before to isolate the population proportion in the middle. So we multiply both sides by this square root of p times 1 minus p divided by n. And then we move the p hat to each side by subtracting and things like that. And then we end up with the confidence interval. Okay? So just to make it clear, here is that confidence interval. Okay? So this is just this piece. And here's the other piece down here. Okay? This is my confidence interval for P, the true population proportion. Okay? And again, it has the exact same, don't worry about all these mathematical details if you're getting lost. All we want to remember is it has the same general kind of construction as before. Our estimate from our sample, critical value times standard deviation, that's the lower bound, subtraction, and then the upper bound, estimate, plus critical value times standard deviation. Okay? That is the key thing to remember. Don't worry about all the mathematical details. Just know the general way that we construct confidence intervals. Okay. All right. And again, you'll notice a very similar problem we had before. And that is, this interval contains a population proportion, p. If we knew p, then we wouldn't have to create a confidence interval for it. So this has that same issue. Remember before we said we didn't know sigma, the population standard deviation. Okay? So what can we do? We can create, this is going to get kind of technical, so again, don't worry if you don't follow all the details. We can create what's called a walled confidence interval. What does that look like? So remember, this is our general formula that we just had, and we said that the problem with it is that it incorporates these population parameters that we don't know. If we knew the population parameters, we wouldn't need a confidence interval. So what is the logical thing to do? Well, we would just replace everywhere we saw a p, we just replace with p hat our estimates. Okay? So the estimate of the proportion is used. Everywhere we previously had a p, we now have a p hat. Okay? This is called the walled confidence interval. And so statisticians spend their time studying all this stuff, and people have shown, several authors have shown, that this interval does not cover the true value 95% of the times when it's repeated, even with large sample sizes. Remember that little demonstration we showed that 95% of the confidence intervals, so if you construct 100 confidence intervals, on average, 95% of them should cover the true population parameter. Well, a lot of statisticians showed that this confidence interval here does not do that, so it's not adequate. Okay? So an alternative to this, remember we use the normal approximation, right? And so where did that come through? The normal approximation is here with these z's. That's where we used the normal, even the 1.96. Okay? We used the normal approximation to the binomial. Well, what if we just scrap that? Okay? And base the confidence interval, we say, no, this is no good. I want to base my confidence interval on the binomial distribution instead of the normal approximation. Okay? So what would that look like? That would be something to this effect. Okay? So, whoops. Okay, so that's what that would look like. Okay, but these intervals are conservative, which means they have coverage greater than 95%, so they might not be the best. And computing this piece, the n choose k, is very difficult, okay, as the sample sizes get large. So that's one alternative, but that's not so great. Okay, and then there are all these other types of confidence intervals that people have suggested. Okay, so that was the binomial confidence interval. There's someone has suggested, some guy named Wilson has an interval. Then there's the Agresti and Cool interval, and so on. Okay. So there's just all you want to take away from this is that there are different ways of constructing confidence intervals for proportions, okay? So proportions with two outcomes, binomial situations. And so all four of these, meaning the normal approximation, the binomial, the Wilson, and the Agresti and Kuhl, all four of these are available in Stata. So again, don't worry about the technical details, just know that there are different kinds, and when you report something, you want to just, when you report a confidence interval for a proportion, you just want to make it clear which one you've used, okay? All right. So the recommendation here is use either the Wilson confidence interval or the default confidence interval for the statistical package you use. Normally the differences are really, really small, so it's not going to be that big of a deal. Just know which one that you used and report it in your paper, okay? So to summarize, for a dichotomous or binary outcome, the estimate of the population probability of success is the sample proportion, and we can place a confidence interval around that just like we did before, okay? So we're finally at the end of this lecture. So what did we learn? We learned to estimate the population mean using the sample mean. We learned about the central limit theorem, which was really cool and showed us that even if we have a skewed distribution, if we keep taking samples from it and calculating the sample means will have a normal distribution, right? Which is centered at the population mean of mu, and which has that spread, which we said was sigma over root n. Okay? A very, very cool result. Very cool, because we only get one sample mean when we collect a sample. We collect a sample, we get one sample mean, and yet somehow this really cool central limit theorem tells us about the variability were we to repeat that experiment over and over again. So we learned about the central limit theorem, then we learned about confidence intervals, and also to estimate the population proportion using the sample proportion. Okay? All right. So the next session will be a Stata tutorial about confidence intervals and so on, and I will see you then.